So we're gonna end this lecture with a vague discussion of three rather complicated subjects. These are the Kerr solution, rotating black hole solution, the so-called no-hair theorem, and so-called cosmic censorship hypothesis. Why are we going to vaguely discuss them? Because their rigorous and complete discussion goes way beyond the preliminary lectures on general theory of relativity. So what we do at best, we will just present some formulas and give physical intuition for those three subjects. So let me start with the Kerr black hole. In so-called Boyer-Lindquist coordinates, the metric for the Kerr black hole looks as follows. It's rather complicated. And I'm going to give the definition for the notations in a moment. But let me write them. Sine squared divided by rho squared dt squared plus 2 kappa m times a divided by rho squared r sine squared theta d phi dt minus rho squared divided by delta dr squared minus rho squared d theta squared, and finally minus a sine squared theta over rho squared d phi squared. So we have to specify the notations. First thing, we're using the following coordinates in space-time. The spherical coordinates in spatial part. That's the first thing. Then delta is just r squared minus 2 kappa m times r plus a squared. Rho squared is equal to r squared plus a squared cosine squared of theta, and a is r squared plus a squared squared minus a squared delta sine squared theta. So one can see here that there are two parameters, m and a, on which the black hole depends. So if we put a to 0, if we put a to 0, this black hole metric reduces to the Schwarzschild one, as one can see. It's not hard to see. Second thing, as r goes to infinity, we encounter the following metric. As r goes to infinity, the metric tensor approximately becomes 1 minus 2 kappa m divided by r. M and a are constant, unlike the previous solution, where m was frequently a function of r. 2 kappa m a sine squared theta divided by r d phi dt minus 1 plus 2 kappa m divided by r dr squared minus r squared d omega squared. So again, from this asymptotic form, one can see easily the following situation. First of all, m defines the mass, because without this term, this just reduces to the same form as the Schwarzschild does reduce, because this, when a equals to 0, this reduces to the Schwarzschild. So m is a mass, and a gives the presence of this term. And also notice that this term, because of the presence of this term, the metric, although it is invariant under the time translations, but it is not invariant under the time reversal, exactly because of the presence of this term. This term makes this metric stationary but not static. So components of the metric are time independent, but there are non-diagonal terms, which this term correspond to the rotational terms. They describe the rotation. So the space-time describes the rotation. So this m times a is the total momentum, rotational momentum. So the physical meaning of a is momentum attributed per angular momentum attributed to per unit mass. And how to see that this term corresponds to the rotation? Well, the first thing is that one can do the following. One can take Minkowski spacetime and make a transformation to the rotational reference frame. Another way is to study closer this metric, and that goes beyond the discussion of this, our discussion. Well, one can find this in textbooks, for example, Landau-Lifshitz, more careful discussion. Now, let us see whether this metric has any horizons or not. First of all, to do that explicitly, one of course has to draw a Penrose diagram, Penrose-Carter diagram for this metric, but that also goes beyond the scope of the present lecture. So we vaguely give an idea what is going on. So one can see that this part of the metric, which is similarly to the Schwarzschild case, blows up when delta is equal to 0. Which corresponds to it's a quadratic equation as follows from here, and it corresponds to r plus minus. Two solutions of this equation are like this: plus minus square root of kappa m squared minus a squared. So, as one can see, as a goes to 0, r plus goes to rg. Schwarzschild radius. So that is one of the hints that r plus is the radius of the horizon. So the horizon of this solution is r equals to r plus. One way to see that is to draw a Penrose-Carter diagram for this solution. Another way to see that is to consider that the tangent vector to this normal vector to this surface, to the surface r equals to r plus, is light-like. Normal vector, and mu squared is equal to 0. Then it means that this is the horizon, because to escape from this surface, one has to have light velocity. So this is the event horizon. Another thing is the following. Look when this term is vanishing. When this term is vanishing. This term is vanishing for the following radius. R0 of theta equal to kappa m plus, so this is one of the solutions of the fact that this is vanishing, plus kappa m squared minus a squared cosine squared theta. Cosine squared theta. So this is so-called the surface of ergo region. Notice that this r0 of theta is greater or equal to r plus. So we encounter the following situation, that we have a sphere horizon at given moment of time. So this is a sphere of the horizon, this is r plus, and we have ergo region, which has this form, it touches at the poles of this thing, and this is r0 of theta. So this is ergo region. One can escape from this part. One cannot escape from here, but one can escape from here. To see that, one cannot escape from here, one has to consider normal vector to this surface and find that it is light-like. And to see that one can escape from this region is to consider, one has to consider normal vector to this surface and again see that it is not light-like. So one doesn't have to have speed of light to escape from this region. Then that is a way to observe, to make these observations. Now one can notice that, so when r equals to this, G00 is 0. G00 is 0. Now, one can see that not always this has real solutions. One has real solutions one has real solutions for this case. And for this case, for this case especially, if kappa m is greater than A. Otherwise, there is no real solution for this guy. And also, one can observe that this metric has closed time-like curves. Closed time-like curves. So this is a rather unphysical situation. And we have a naked singularity, because there is no solution for this equation. There is no real R plus. It means that no horizon. But at the same time, we have a singularity. So this metric, the space-time has a singularity which is not surrounded by the horizon. The explanation why goes beyond these lectures. I do not give explanation for that. But it is unphysical to have such a situation that, that there is a singularity which can be reached within finite time from the point of view of an observer which stays always outside of the body, of the black hole. So there is so-called cosmic censorship. Physicists believe, physicists those who study black holes, believe in so-called cosmic censorship, that in real situations, during collapse, one cannot create such an object, so described by this metric, with kappa m greater than 0. When kappa m is equal to A, it's called critical solution, but one cannot create such a metric which corresponds to this situation. Or more generally, it states that during real physical situation, one cannot create space-times with the singularities which are not surrounded by horizons, event horizon. Why? Well, one believes that in real physical situations, starting from generic conditions which are smooth, so we have at our disposal something smooth initial metric, smooth initial matter distribution, smooth forces, etc., etc. And then we, using various devices or tools, want to create from this matter some black hole-like object. And physicists believe that using all possible tools, we cannot create something which will have a singularity which is not surrounded by event horizon. Well, this is just a generic belief, sounding like possible, although as far as I understand, there is no rigorous proof of this statement from first principles. And the proof should rely on the fact that we shouldn't go beyond the general theory of relativity, because like if we can prove that using some other higher theory, which includes general relativity, it's a separate story. The question is whether one can prove this statement within only general theory of relativity. So, and last thing which remains to be said at this point is the following. We want to describe so-called no-hair theorem. No-hair theorem says the following thing, that if we have only general theory of relativity plus matter, no any electric charges, etc., so within this theory, any collapse process, generic collapse process, will lead eventually to such a metric, which is described by only two parameters, by mass and angular momentum, and nothing else. So the reason for the belief in this no-hair theorem is actually very simple, can be explained in simple terms from my mind. And let me just give you the idea why it is so. First of all, as I have explained in the previous lectures, the Schwarzschild horizon, or the horizon of a black hole, is the surface of infinite redshift. Infinite redshift. Why? Let me explain that on the Schwarzschild Penrose diagram. So on the Schwarzschild Penrose diagram, it can be obviously seen that if we have anyone who is staying very close to the black hole horizon, very close to the black hole horizon, it can stay fixed at a fixed radius. And if something inside the black hole creates a radiation or makes some crazy motion, like masses or charges, any radiation will go towards singularity. It will not go outside of the surface. So we have a very funny situation. Whatever happens on the horizon or just behind the horizon, whatever crazy motion happens, whatever crazy radiation is created just inside the horizon, an outside observer at whatever radius it stays, will never see any radiation. It will see only static fields, only static or stationary fields. It is very important. So the Schwarzschild horizon, the horizon of the black hole, is the surface of infinite redshift. Infinite redshift. Let us study it from the point of view of a collapse. If we have a collapse, the matter of the black hole falls down the creation of the horizon, approaches its horizon. And of course, during the collapse process, there are a lot of radiation processes happening, so many things are radiated. But as the source of this radiation, the collapsing matter, approaches the horizon, the radiation influences stronger and stronger redshift. So you see, if there is a radiation which is created very close to the horizon, it performs the work against gravitational force, and because it performs the work against gravitational force, its energy is reduced, and because of the reduction of energy, the frequency, which is proportional to the energy for the photons or for the gravitons, the frequency is redshifted. So we have a stronger and stronger redshift. Related process to this fact is the following, that during the creation of the black hole, during the collapse process, everything that can be radiated is radiated away, and all the higher multiple momenta during the collapse process are decaying with time. It means that the body which remains during the collapse, after the collapse process, has all the momenta which are responsible for the radiation reducing in time, are radiated away. So what remains at the final stage of the collapse, can carry only stationary fields. Notice that to have a electromagnetic radiation, one has to have dipole moment changing in time. Changing in time multiple moment or electric charge, monopole moment, electric charge doesn't create radiation. Electromagnetic radiation. As we will see in ninth lecture, to have the gravitational radiation, one has to have changing in time quadruple moment, even more. So rotating angular momentum doesn't create radiation. Gravitational dipole moment doesn't create radiation. And gravitational monopole moment, mass, doesn't create radiation. Again, let me tell it in a different way. Suppose you have in electromagnetism, you have a sphere, ideal sphere, which is homogeneously distributed electric charge over it. This sphere is breathing, so it like goes outside, so it shrinks and expands, respecting spherical symmetry and homogeneity of the charge distribution. Independently of the radius of this sphere, it always creates outside of it Coulomb field. So electric field is not zero, but magnetic field is zero. So it means that such a sphere, despite the fact that the charges are moving with acceleration in this motion, this sphere, breathing sphere, never creates electromagnetic radiation outside of it. It's known by those who are building antennas. They know that spherically symmetric antenna cannot be created. So that is related to the fact that to have electromagnetic radiation, you have to have dipole moment changing in time. While for the sphere, breathing sphere, dipole moment with respect to its center is always zero. And actually, all multiple momenta with respect to its center are 0. So similar situation we have in gravity, and even more refined, in the sense that spherically symmetric mass, when it breezes, doesn't create gravitational radiation, because outside of it, in Newton gravity, it creates Newton field. In Einstein gravity, it creates, due to Birkhoff theorem, creates Schwarzschild field. So these are very interesting situations. So again, let me say what happens. During collapse process, everything that can be radiated is radiated. What remains is the object which is characterized only by 3 charges, by mass, angular momentum, and if there is electric charge, by electric field, by electric charge. So these are the only charges which cannot create electromagnetic or gravitational radiation. All the rest of the multiple momenta can create radiation, and they are radiated. These are not. So this fact relies in the basis of the no-here theorem. In the absence of the electric field, when we don't have this, we have the solution which is characterized only by 2 parameters, by mass and angular momentum, as a result of the collapse process. That is the statement of the no-here theorem.